to me, but there you go. last clock change. So for anybody who hasn't seen me before, my name is Ben Church. I'm a geologist, which means that I combine all of the sciences to arrive at an understanding of the way in which the Earth works. So in a previous life, I worked on oil rigs. I then was a teacher for 26 years, teaching both geology and geography, and I now lead adventure travel expeditions and do a variety of other things, more pies and fingers. So here's the Earth. What's inside it? What do we know about what's inside it? What's the evidence for what's inside it? How can we interpret the evidence? And with science, it's always about asking the right questions. So what I'm going to run through this morning is we'll think about, well, what can we directly sample? What can we actually grab a hold of that's from within the Earth? We'll think about the science of earthquakes, seismology, and how they can give us information about Earth structure. We'll think about the layers of the Earth, and we'll look at the crust, the bit on the top, the lithospheric tectonic plates that shift around over the layer called the asthenosphere, which is just a few percent molten. We'll go deeper and look at the mantle, and we'll look at the core. And finally, we will consider the composition of the inner Earth. So in 1864, Jules Verne had this science fiction novel, Journey to the Center of the Earth. So this German professor, Otto Lindenbrock, he went down some volcanic tubes on the Reykjanes Peninsula in Iceland, and he took his nephew Axel and a guide, Hans, on this adventure. And they went into the Earth in Iceland, and they came out at Stromboli in Italy. And they had many adventures along the way, prehistoric animals, all sorts of hazards and stuff. But this was 1864. They had the excuse that very little science was known about the internal Earth. If we then look at the movies, so we've got the 1959 James Mason, Pat Boone movie, and then we've got the one in the middle there, in 1989, sort of aimed at a teenage audience, and then 2008, there was a 3D version. They've got no excuse, because by then we did know the science. So what I'm going to do is use science to tell you a story. An exciting and sometimes surprising story, which does include, certainly near the beginning, lots of world records. And I hope to give you a bit of an understanding of how science works, how we can get these facts. It's, being a geologist, a bit like being a detective, but instead of arriving on the day of the crime, you're arriving millions of years after the event, by which time a lot of the evidence has either been completely destroyed or it's been effectively tampered with. Now, if a mechanic saw this, he'd go, well, how am I going to fix that? How much is it going to cost? But for scientists, we need to ask different questions. So if we look at this, and the scientists will then, well, now, what actually happened here? A parked car was hit by a rock, 12.5 kilo rock. Where did it happen? Peaks Hill in New York. When did it happen? 9th of October, 1992. Why did it happen? It was a meteorite impact. Who was affected? Miss Michelle Knapp, the owner of the car. And what happened next? Well, this 1980, rather battered Chevy was worth about $500. She sold it to a meteorite collector for $10,000, and the car has been traveling the world ever since, going around exhibitions, Arizona, Paris, Switzerland, Germany, Tokyo, you name it, it's been there. So what? Well, we'll find out a little bit more about our meteorite later in the talk. This iconic image, it became known as the Blue Marble, taken in 1972 from 29,000 kilometers up, shows us the Earth. So we're going to take a scientific journey now to the center of the Earth. So, as I mentioned in the intro, we'll start with where we can actually go. Well, we could look down a man-made hole. Welcome to Bingham, Utah. This is an open-cast copper mine. It's 1 kilometer deep. The red circle is a super truck. The wheels are about this big. And that's me in the, oh, that's me in the jaws of one of the front loaders that fills it. So that's a kilometre. Okay. 2008, I was lucky enough to visit a cave called the Grooteberge, which between 1953 and 63 was the deepest cave in the world. It's in the Vercors in France. This cave, 1.1 kilometres deep. Verkhovkina Cave, currently the deepest cave. This is in Georgia, between Russia and Turkey, at the sort of eastern end of the Black Sea. 2.2 kilometres deep. Maybe we could go down a mine. So the Maponing mine in southwest of Johannesburg in South Africa. It's a gold mine. They extract about 5,000 tonnes of rock a day. There's about 8 grams a tonne of gold in that rock. So they're getting £2 million worth of gold out every day. It's deep, and temperature increases with depth. So it's very hot down there, about 55 degrees C, 131 Fahrenheit. So what they do is they pump a slurry of ice and salt down the mine, and then they have huge fans blowing air over the ice, which brings the temperature down to a still rather balmy 28 degrees. And if you're working hard in those conditions, it's going to be very unpleasant. This mine is 3.9 kilometres deep. And the workers go down in a lift, takes 6 minutes. The lift goes down at 36 miles an hour. You can find out some nuts facts when you're researching these talks. I mentioned at the beginning that I used to work on oil rigs. And if I was working on a rig in the North Sea, the borehole would typically be about 3 kilometres deep, sometimes a little more. What about the deepest ones? Well, the deepest boreholes for a very long time was on the Kola Peninsula in Russia. And it took them 20 years to drill this borehole. It's about 23 centimetres, about 9 inches in diameter. And this borehole then, as you can see there, 12,226 metres. Well, it was the deepest borehole in the world. 2012, they did another well called the Chavo well, and this is now another 150 metres deep, so at 12,376 metres. Now, some of you will have been lucky enough to see gorgeous girlfriend Callie's talks about diamonds. Now, she will have told you that diamonds are found in kimberlite pipes, and these are the remnants of ancient volcanoes which have a very deep magma source. And in that deep magma source, from the magma chamber, fragments break off the walls of that magma chamber to become included in the magma, which is then erupted at the surface. And these, what are called xenoliths, bits of rock from the mantle, we think come from a depth of as much as 30 kilometres. So that's getting a little bit deeper. So if the Earth's radius is 6,378 kilometres, which, if you were walking at 5 kilometres per hour, would take 53 days to get to the centre of the Earth, or if you were driving a car at 100 kilometres an hour, it'd still take you 64 hours. That means that our deepest borehole, at just over 12 kilometres, let's say 12.5 kilometres, is less than 0.2% of the distance to the centre of the Earth, which is a bit like imagining a postage stamp on a football, or a mosquito might bite on an elephant's bum. So we haven't got very far. I've got a question for you. How many people have ever had an X-ray, or a CT scan, or an MRI scan? Now, all of those things give us information about inside the body without going there. And that concept, that idea that you can find out information about what's inside something without going there is really important. What we're talking about is the concept of remote sensing, and the geological equivalent of X-raying the human body is using earthquake waves, what we call seismic waves, to work out the structure of the Earth. So here we had in September this big earthquake which unfortunately killed 3,000 people in Marrakesh. So this is the actual effect of an earthquake. So how does an earthquake actually work? Well, in 1910, Harry Fielding Reid studied the San Francisco earthquake of 1906, a big earthquake, a huge amount of damage, much of it caused by fires following the earthquake. And he came up with what is generally accepted to be the way in which earthquakes work. It's called the elastic rebound theory. So you have directional stress being applied to rocks. The elastic strain, the response to that stress that's been applied, can be stored for tens or hundreds or many thousands, tens of thousands of years. When the stress exceeds the friction, then that elastic strain energy that's been stored up for all that time is suddenly released at 3.5 kilometers per second, and the rocks will break, they'll fracture, and this gives us a fault. Now, typically, you get a few little bits of movement along that line before the main event. So you'll get foreshocks, then you'll get the main event, the main earthquake, and then you'll get aftershocks. And the point where that fracture actually starts, where the earthquake is born, if you like, is known as the focus, and that is below the surface. The point on the surface directly above that focus is known as the epicenter. Now, if you think of a wave, you will probably, as you're on a ship, think of a surface wave, like waves on the sea. And the seismic waves that cause the damage in an earthquake are actually surface waves. They have a kind of a rolling motion, if you like. So we have the Rayleigh waves, which have both compressional and shear elements, and also, and my students used to love this, the love waves. And it's actually the love waves that cause all the damage in an earthquake, and these are primarily shear. But they only go through the surface. These only travel through the crust. Now, if you look at this diagram, it's a plot of the arrival of different types of earthquake waves, of seismic waves. And those surface waves, they're the ones with a really big amplitude, the ones that go up and down a lot. But you can see that to the left of those, you've got two other types of waves, the P and the S. P for primary, because they get there first, and imaginatively, S for secondary, because they get there second. So the P waves then are faster than those surface waves. And this is actually a plot of another San Francisco earthquake, the Loma Prieta earthquake of 1989. So these P waves, the primary waves, these ones vibrate in the direction of movement, and they cause the material that they affect to compress and expand. I mentioned that they arrive first. They're 1.7 times faster than the S waves, and they will travel at about 5 kilometers a second in a rock like granite. The S waves, S for secondary, 1.7 times slower, they deform the rock at 90 degrees to the direction in which the wave is traveling. Now, what is really important here, hold on to this thought, is that S waves will not travel through liquids, because the liquids don't have any shear strength. And that's what makes the earthquake waves really, really useful. So I asked my students once in a lesson, I did a bit of a review of the previous lesson, how do you measure an earthquake? With a very big ruler? No. The instrument that you use to measure earthquakes is known as a seismometer. And the earliest record we have of a seismometer comes from 132 AD by a brilliant mathematician and scientist in the Han Dynasty, Chang Heng. And what happened here was that the dragons had hinged mouths containing marbles. And if there was a movement of the earth, then the jaws would open and the marble would drop into the mouth of one of the frogs. And then you could determine which direction the shock waves had come from. A modern seismometer is not quite such a pretty beast. It looks just a bit like a big can of baked beans. You've got a very heavy magnetic mass, and then inside that, you've got some coils of copper wire. Now, the seismometer is anchored very firmly to the ground, and when the Earth moves, that, because of inertia, the magnetic mass stays pretty stationary, but the relative movement of those coils generates a very small electrical signal. These are extremely sensitive. They could detect a chicken pecking corn 10 meters away. And because they're that sensitive, we normally put them down a borehole to isolate them from surface effects like trucks going past and so on. So the seismometer is the instrument which detects the seismic waves and produces an electrical signal. Very small, but this is then amplified. It goes to this instrument, which is a seismograph, which records the Earth movements. And the actual record, the piece of paper with the wiggly line on it, is our seismogram, the trace. This one, which I've already showed you. So that's a seismogram. Now, as you go into the Earth, we know by looking at rocks, even in the shallow 12.5 kilometers that we can look at, that the density of the rocks increases. And we also know that the seismic wave velocity will decrease as rocks get denser. However, little exercise that I used to do with students. So if I'd had a naughty student, I'd said, right, I want you to bite the end of the desk here, please. Right? And I used to have one of those old watches that ticked. And I put the watch on the thing. I said, oh, can you hear that? And they could detect it, and they were amazed. And then I'd rap the table, and they'd go, oh, why did that happen? When I hit the desk, you know, they could feel it through their teeth. And I said, would that have happened if it was a rubber table? And they'd go, well, no. Well, why is that? Well, the reason is that if you've got something which is incompressible, that increases the velocity of the seismic waves. If you've got something which is rigid, it will increase the velocity of the seismic waves. And those effects override the effect of the increase in density with depth, because material gets more incompressible and it gets more rigid with depth, at least to start with. So this is the first little bit, this is my first reveal of a diagram of what happens with seismic waves as we go into the Earth. So generally then, because of the increase in rigidity and incompressibility, these seismic waves are getting faster and they travel along curved paths. So when you look at this, why does the pencil look bent? Well, it's a phenomenon known as refraction. So here we've got, if you're going from a less dense to a more dense medium, then the waves get bent. So the light waves get bent, and it looks like we've got a bent pencil. Now, if we've got a seismic discontinuity, if we've got a boundary between rocks with different properties of incompressibility and rigidity, the same thing happens. Those seismic waves will be bent or refracted, sorry. So they can be refracted, bent, or they can sometimes be reflected. And if you're going from a less rigid to a more rigid, a less incompressible to a more incompressible medium, so the seismic waves are going to speed up, then that refracted ray will move away from the normal, the line at 90 degrees to the boundary. Conversely, it'll go towards the normal if you're going into something which is slowing down the seismic waves. Now, the first real use of this information was by this chap. He was a Croatian seismologist called Andrija Mohorovičić, but everyone calls him Moho for short. And he discovered a seismic discontinuity, the boundary between the crust and the top of the lithospheric mantle, which is what the rigid part of the mantle, which is part of the lithospheric plates. He recognized that there were two sets of P and S waves that were detected from an earthquake. One set that just went directly through the crust, and another set that went down through the crust, into the upper lithospheric mantle, then it went along, having been strongly refracted, and then popped out again at the detector. Now, what happened is that if your seismic detector, your seismometer, is close to the source, the seismic source, then the direct waves would arrive first. But if you went further away, although the distance was greater, because you'd got refracted waves going very quickly through that upper part of the mantle, they would actually arrive first. And this layer then became known as the MOHO, the depth to the base of the crust. And the depth to the MOHO does vary. It depends on what kind of crust it is. So if you're looking at continental crust, generally it's on average about 35 kilometres or so. But it's a great deal more, maybe as much as 90 kilometres if you're underneath a mountain range like the Himalayas. If you're out in the open ocean, the oceanic crust is much, much thinner. It's only about 7 kilometres thick, something like that. So both the P waves and the S waves go through the upper mantle below that MOHO. So what does that tell us about the physical state of it? Well, the P waves, they can go through solids and liquids, but the S waves can't go through liquids. So we can conclude that that layer below the crust, the upper part of the mantle, the lithospheric mantle at least, must be solid because it transmits the S waves. Excuse me. So, if we go then into that layer, we know that it is incompressible and it's rigid. The lithospheric mantle then varies a great deal in thickness, and it is reflected by the thickness of the crust as well. So generally, if you're right at the mid-oceanic ridge, it might just be a few kilometres thick, but underneath a mountain range could be as much as 200 kilometres. But generally, it's between 100 and 200 kilometres thick. So, a little bit more of our graph revealed. As we go down with depth, we get to a depth of between 100 and 300 kilometres depth, and the seismic waves slow down. So this is known as the low velocity zone, or LVZ for short. So why do they slow down? It must be solid because the S waves are still going through it. Well, what we think is that while it is still pretty incompressible and it is pretty rigid, it's a little bit less rigid. The S waves are slowed down by about 6%. And we think that this is a reflection of the fact that at the base, when we get to this layer, we're around about the 1,300 degree isotherm, which is the temperature at which we start to get a little tiny bit of partial melting of the upper mantle. So in that low velocity zone, we've got maybe 3, maybe 4% melt. Still solid, but it's just got enough liquid in it for, on a geological time scale, for it to flow. You might remember the analogy that, although it's temperature-wise very wrong, ice is a solid and it can flow several meters a day, whereas the asthenosphere is a solid, but it can flow a few centimeters a year. So we've got the rigid crust, we've got the rigid lithospheric mantle, and then we've got this asthenosphere layer, the low velocity zone. So it's moving by plastic deformation. Over millions of years, these hot, solid rocks can flow. So what happens to the seismic waves below then? Well, they increase in velocity because we're returning, thanks to the immense pressure, to a situation where everything is in a solid physical state. And that carries on all the way down to 2,900 kilometres. 1906, Richard Oldham, a seismologist, he discovered what he referred to as shadow zones. Zones where if you had a big earthquake and you had detectors over the globe, there would be no seismic waves detected. So for the S waves, you're looking at anywhere below about 103 degrees from the epicenter, there'd be a shadow zone. A bit like shining a torch through a transparent ball with a tennis ball in the middle of it, there'd be a shadow. The P waves, though, had a ring-shaped shadow zone. And he explained that by saying, well, maybe the S waves, they can't go through liquids, so maybe when we get to 2,900 kilometers depth, we've got a liquid core. So the S waves would be completely stopped by that because liquids have no shear strength. But the P waves, they're going from into a medium of different incompressibility, different rigidity. So they will be bent, they'll be refracted. So they will come out on the other side of the Earth, but there'll be this ring where you don't get any of these P waves. In 1912, there's another seismologist called Gutenberg, a German-American, and he became attached to this discontinuity, and it became known as the Gutenberg discontinuity. So that's our core mantle boundary. Introducing a female seismologist. Okay, so this is Inge Lehmann, who was a Danish seismologist, and she did a lot of work on a 1929 magnitude 7.8 earthquake in New Zealand, the third deadliest earthquake that they've had. And looking at the data from earlier, the proposed dense liquid core would mean a complete shadow zone. But what she found was that you did get a few P waves in that shadow zone. And this diagram, which I've adapted slightly, is actually from her paper in 1936. So you were getting a few P waves arriving. And she theorized that these had been generated by a solid inner core. And the discontinuity, the boundary between the inner core and the outer core, became known as the Lehmann discontinuity. Why solid? Because of the immense pressures there. It could only exist as a solid. So Gutenberg and Richter, they modeled the effects of a solid core, and they confirmed that Lehmann was right. A little aside here for a moment. You may be familiar with Charles Richter. Came up with the Richter scale for measuring earthquakes. The scale is a scale of the amount of energy that is released, the amount of kilograms of TNT equivalent. But if you're a hazard geologist, that's really not all that useful for hazard management and mitigation. The reason being that what you need if you're going to manage hazards is to have a knowledge of the amount of ground shaking, because that is what's going to give you the damage. So the Mercalli scale is much better. It's an observational scale about how much the ground shook. Why is this important? Well, you could have two earthquakes with the same Richter scale value with very different Mercalli scale values. And this is all about the geology, about the ground conditions. You need to know the ground conditions. If your buildings all have foundations on very solid rock, they will shake with the quake. But if your buildings have foundations on unconsolidated material, loose material, for example, lake sediments or river sediments, loose sand, then you'll get a very different response. It's a bit like if you're standing in the surf and you wiggle your feet in the sand, your feet sink in a bit. It's like quicksand. And during the period of shaking, during an earthquake, that is how the ground can behave. So this phenomenon is known as liquefaction. The ground is behaving like a liquid. So here in Japan, at Niigata in 1964, these buildings were built on unconsolidated, on loose sand. And when the earth shook, momentarily, it behaved as a liquid. So the buildings just toppled over. And there were reports of people just opening the window and walking down the front of the building. Remarkable. So 3,500 buildings were destroyed in this event. But luckily, only 36 people lost their lives. In 2005, with the development of even more sensitive seismographs, there was further proof of there being a solid core. And we've got only the P waves going into the liquid outer core, but we think that when they hit the inner core, which is solid, they actually generate some S waves, but then only P waves come out the other side. So now we know the depth to the different layers. What's the Earth actually made of? For the rocks of the crust, it's relatively straightforward because we can directly sample those rocks. For the rocks of the top of the mantle, well, we can go back to the kimberlite pipes and we can get the xenoliths, the strange rocks that have come from the walls of the magma chamber, which give us a sample effectively of the upper mantle. 2,200 years ago, the Greek polymath Eratosthenes made the first measurement of the distance around the Earth's sphere. And it's been clear ever since that it's a sphere and it's got a centre. We've known for a very long time that we don't live on a disk, and the myth that medieval people thought that the Earth was flat just came from Victorian anti-religious propaganda and the misinterpretation of medieval maps. But if we know the proportions of the Earth and we know some of the properties of the Earth, then we can use that to interpret the Earth's structure and its composition. Remember, we have to ask the right questions. So is the rock made out of the same, is the Earth, made out of the same rocks that we find at the surface? Well, if you look at a sugar cube, that's got a density of 1.4 grams per cubic centimetre. So if it was a cubic centimetre of water, that would just be 1 gram. Now, rocks have a density of double that of a sugar cube. So that would suggest, then, if the rocks at the surface of the Earth are about 3 grams per cubic centimetre, that the density of the whole Earth would be around about that. Notice the iron. Hold on to that thought. So, who's this guy? Well, this guy is Newton, Sir Isaac Newton. He came up with Newton's law of gravity in 1687, the force of attraction between two objects. So the denser something is, the bigger the force of attraction, and the more mass that an object has, the bigger the force of attraction. And the force of gravity allows us to calculate the mass of the Earth. And in 1798, Henry Cavendish put together the final nail in the coffin of the hollow Earth, because he calculated Earth's gravitational pull, and that made it possible to have the first pretty accurate calculation of the mass of the Earth. And by knowing the mass of the Earth, we can also calculate its density. So the density of the Earth, you will see, 5.5 grams per cubic centimetre. Well, that's interesting, because the rocks at the surface are only 3 grams per cubic centimetre. So what on earth could there be, if you pardon the pun, inside the Earth which is dense enough to bring the bulk density of the whole Earth up to 5.5? I talked about the Earth's properties. Well, the Earth has a magnetic field. And magnetic fields generally are related to things that contain ferrous material, iron. So maybe we could argue that there's some dense metal within the Earth, possibly iron. So remember, the iron has a density of 7.9 grams per cubic centimetre. So is there any other evidence other than the fact that the Earth's got a magnetic field? Remember this? A meteorite. Most of the meteors that you see, the shooting stars, are caused by only pea-sized meteorites. And they're very, very common. There's a sort of constant rain of between 40 and 80,000 tons of meteorite material arriving on Earth each year. About maybe 20 or 30,000 of these weigh more than a pound coin, so more than roughly 10 grams, something like that. But they're not commonly found because we've got 71% of the planet is covered with water. So they're not commonly found, and if there's areas with vegetation and stuff, they're going to be difficult to find. But they can be found, excuse me, in Arctic areas, Antarctic areas, show up well against snow, and also in desert areas, so for example in Australia. It's very, very rare to witness a meteorite fall. Throughout all of history, we've only got about 1,400 witnessed events. In 1954, a grapefruit-sized 4-kilogram meteorite hit the house of Anne Hodges, and it bounced off the furniture and landed on her. Luckily, she wasn't too badly hurt. In 2009, Gerrit Blank, a 14-year-old German boy, was walking to school, and he was hit by a tiny meteorite, and it grazed his hand and left a smoking crater, 30-centimetre little crater there. Well, we can actually see these meteorites, and we can cut them in half. We can have a look at them and find out what they're made out of. At the top, we've got what are referred to as stony meteorites, and they seem to have a composition quite similar to what we think is the composition of the Earth's surface and the mantle. But at the bottom, we've got a different kind of meteorite, a very dense iron meteorite. These are made of iron and nickel, and the specimen that you've got at the bottom right has been cut to show the internal crystalline structure of it. So iron and then about 6% nickel. And we think that this is what makes up the core. So how can that be? Why is this evidence? Well, when we had the origin of the solar system, we had a nebula, a rotating cloud of dust and gas. And this then started to contract, and we got these particles colliding and forming eventually the planets. The bits that didn't make it to making a planet formed the asteroid belt between Mars and Jupiter, and that's where the meteorites come from. So they're a sample of what was left over when the planets were made. So how did all of that iron get to being deep inside the Earth? Well, when we had the original formation of the Earth, the gravitational compression would have generated heat. The meteor bombardment, the knocking together of all of those particles, just like when you do rapturous applause at the end of a talk and your hands get hot, would have generated a great deal of heat. And on top of that, you would have also had natural radioactive decay. So the early Earth then, forming about 4,600 million years ago, would have heated up. It would have heated up a lot. So that about 4 billion years ago, we had the iron catastrophe. The whole planet melted. And that very dense material, the iron and nickel, sank towards the middle to form our inner core and outer core. And the less dense material would have differentiated, would have moved towards the outer layers of the Earth, giving us the layered structure that we have today. And the oldest crustal rocks that we have are just around about 4 billion years old, from the Great Lakes area of Canada. So we've got here then the less dense elements concentrated in the crust and the really dense iron concentrated within the core. The exact nature of the inner core is still subject to debate. The enormous pressure, over 3 million times atmospheric pressure, means that materials there will act very differently to surface conditions. So you can only kind of hazard a guess, really, at what's going on down there by experimentation. Introducing the diamond anvil, where you've got the points of 2 diamonds, very, very tiny points, applying force to a very small area. How many of you have ever had somebody tread on your foot? If it's a normal shoe, little bit uncomfortable. If it's a stiletto, oh my goodness. Why? Because if you concentrate that force into a small area, you're exerting a great deal more pressure. And with this device, with the diamond anvil cell, we can generate an enormous amount of pressure. So we can simulate what it must be like at the Earth's core. And we think then that down there we have got a solid iron-nickel core at a temperature of about 5,400 degrees C, similar to the surface of the sun. So, what a journey. We've got a model now of the layered structure and the composition of the Earth. Please note, this diagram is not to scale. Very common that people put books and so on, or do programs on TV about Earth structure. They don't put a scale on, which is really annoying. Let me introduce to you a scale model. So, you can see here the thickness of the crust and the lithospheric plate relative to the whole Earth. This is on the first sheet of a roll of toilet paper. You'd have to unroll the entire roll to get anywhere close to the centre of the Earth. So, we started with fiction, but we've done a lot of geological detective work, and now we know that by direct sampling, holes, caves, boreholes, kimberlite pipes, we can sample down to about 30 kilometres depth. That by remote sensing, the geological equivalent of an X-ray, we can use seismic data to tell us the depth to the different layers of the Earth. By looking at the properties of the Earth, by looking at gravity, at density, at magnetism, we can suggest that we've got an iron and nickel core. And then we can look out of this world. We can look at meteorites to confirm that, yes, we have got an iron and nickel core. And we can explain the layered structure of the Earth by the iron catastrophe. So, hope you've enjoyed your journey to the centre of the Earth. I have one more talk to deliver, which should be tomorrow. Please check the Daily Times for the time. It's almost certainly going to be in here. And as it's at the end of the cruise, I thought I'd save extinction till the end. So on a cheery note, I will be talking tomorrow about meteors and dinosaurs, the demise of the dinosaurs. So thank you to the technicians. Thank you for coming. And if you do have any questions, I'll be there at the back. And if you have a question 5 minutes, 5 hours, or tomorrow, then do stop me around the ship. Thank you very much.